All right, thank you very much. So this talk's going to be a little different from others in this session. It's really more of a laser talk, I confess. Just to upfront acknowledge, so Jess Farland and Maggie Ferrari are two undergraduates in my lab majoring in bioengineering. And as always, I got to advertise Union College, small undergrad-only institution in upstate New York, just 2,000 undergrads, with a nice shot of campus in the fall. So it's a nice time of year. All right, so as far as photoacoustic microscopy of lipids, as was nicely described in the previous talk, right, you generally want to have laser pulses near 1210 nanometers to coincide with the peak optical absorption of a lot of lipids. So the usual way to do this is to use OPOs, right? So they are impressive systems, but they're big, bulky, expensive, tend to have slow wavelength tuning and low rep rates. So for microscopy, we want higher rep rates for faster acquisition. So the approach that we have been hammering away at is to start with a compact high rep rate laser and then use nonlinear fiber optics to create the wavelengths that we want. And then you can use a tunable filter to pick the wavelength that you want for imaging. So as far as how do you create the new wavelengths, so we've been using stimulated Raman scattering, and so that describes how a laser interacts with the vibrational modes of the medium. So for an optical fiber, it's glass, right? So as your initial pump laser interacts with the glass molecules, is that you will get a frequency downshifted light due to inelastic scattering. And so as these two optical waves co-propagate through the material, is that you get a gradual energy transfer. And so then by the end, what's called a Stokes wave is greatly amplified. And this frequency shift in silica is around 13.2 terahertz. What can also happen is that you can have a cascaded effect, basically a sequential generation of new Stokes waves, meaning that what we have here can be intense enough to create another Stokes wave. And so that can be cascaded, and so again, you start with this in the beginning, right, and then you create another Stokes wave, and then this becomes strong enough to create a second one, and so on and so forth. So last year we had presented a source where we started out with a 1064 nanometer ND-YAG laser, very common. We sent it through about 20 meters of single mode fiber, and so as far as the wavelengths we got out, these were the cases. So we started out with 1064, and the third Stokes line was about 1238 nanometers, which is definitely longer than what we want. And as far as the input energy was 8 microjoules, 0.6 nanosecond duration, so it's much shorter duration than what we need. So the new version has a different laser. We have a 1047 nanometer laser, so it's an ND-YILF, and that's also commonly available. The fiber is different. We send it through about 95 meters of a graded index multi-mode fiber. We'll talk more about that shortly. But as far as the wavelengths, again, is that we start out with 1047, and then that third Stokes line is at 1215 nanometers. So that's much better as far as being closer to the lipid absorption peak. And the pump laser is much stronger in terms of energy, has 140 microjoules and 14 nanosecond duration. So as we'll see shortly, the energy here is much better for practical applications. As far as just a quick tutorial on graded index multimode fibers, most of us are probably familiar with the usual case, which is called a step index, right? The core has a very uniform refractive index profile. Graded index has a parabolic refractive index within the core. So it turns out that's actually very advantageous for optical communications, because it turns out that the different modes, optical modes that can propagate in a graded index fiber basically travel at the same speed. So that's important when you're sending information. But for our application, what's very interesting though is that the stimulated Raman scattering exhibits what's called a beam cleanup effect in graded index fibers. And so what that describes is that even if your input is a multi-mode structure, not the greatest beam profile, the output, meaning your Stokes waves, tend to be very well behaved, almost Gaussian-shaped beams, right, which is certainly very nice for imaging. And as far as the actual size of this beam, or the mode in the fiber, so we're using a 50-micron diameter core, 0.2 numerical aperture fiber. It turns out it's about 13 microns is the size of the fundamental mode. In terms of the spectrum that we get out of the fiber, is shown here. So this large peak in the beginning, that's the input at 1047. You can see the sequential generation of the 3 Stokes lines. You get a little bit of the 4th one over there. In terms of, if you vary the input pulse, then you're going to influence how many spectral lines you get out. So the bottom row here is the maximum case. So you see the pump and then these 3 Stokes lines here. And as you reduce the input energy, as you can imagine, you get less and less, fewer and fewer lines. So that's just basically to show the sequential manner. And in terms of actual energies, if we stick bandpass filters, these are the ones that we have in the lab, right at the pump is that we have about 60 microjoules left at the output of the fiber, and we have about 12 in the first Stokes line, 9, and then we have about 7 microjoules in the real target wavelength. And so that's good for situations where you are, for example, have an integrated OCT and photoacoustic system, and so you're going to focus your excitation anyway. So having about 7 microjoules of energy is plenty for that kind of so-called optical resolution photoacoustic microscopy system. In terms of the actual spatial modes coming out of the fiber, again, the initial pump laser doesn't look all that great in terms of the beam profile. And so again, as far as if we were to, let's say, plot the horizontal case, it has a lot of structure to it. But for those first 2 Stokes lines, it looks much nicer, right? It's round, looks very Gaussian-like for those 2 Stokes lines, right? And so again, it's very Gaussian shaped. And again, for the longer wavelengths, it's also a very nice looking beam shape, right? And again, as far as the profiles, they all follow a very similar type of Gaussian shape. So indeed, the beam cleanup definitely seems to be happening, so that's good from an imaging viewpoint. To actually measure the spatial resolution, we just imaged USAF target, right, and computed the usual edge spread and line spread functions in both directions, right? This is the usual kind of case that you would do. And so again, we just define the full width half max of the line spread function as our resolution. And so as we get, again, in terms of the numbers at the shortest wavelength, which is your initial, right, it's about 63 microns. But meanwhile, it's much smaller, or definitely smaller, at the longer wavelength, about 43 microns. And again, this is not surprising because we know that the spatial beam profile is not so great at 1047 nanometers. Meanwhile, it's much a little tighter because your beam is a well-behaved Gaussian shape. As far as does this number make sense, right? Again, we can estimate what it should be in terms of this is your actual mode size coming out of the fiber. And here we have a magnification factor. That's because we're using a lens of focal length f1 to collimate the light coming out of the fiber, and we're using another lens of focal length f2 to focus it into our object. So you basically have an imaging system, right? You're imaging the tip of your fiber onto your sample. So if you plug in the numbers, it turns out that we actually get 43 microns. You know, lo and behold, that's pretty good agreement, at least in my opinion, in terms of what we estimate we should get versus what we actually measure. So that was kind of a nice result, perhaps lucky. As far as actual lipid phantom imaging, we just have a simple transmission mode set up just for now. We're in the process of converting to reflection mode. So we have a 25 megahertz transducer for detection, and we just have a little pat of butter inside 2 about millimeter thick layers of chicken breast. So that's our phantom. We scan over a 2 by 1 millimeter region, no signal averaging. And so as far as the images we get, these are shown over a 20 dB scale, that indeed we see the butter very easily at 1215 nanometers and not at the other wavelengths. And we got a little speck of dirt that got in there, right, that shows up everywhere. But as far as the desired result, right, at 1215, that's definitely what we got. One thing to think about is, as mentioned in the previous talk, right, is that if you want to change the wavelength for spectroscopy, right, how would we do that? Right now we cannot because we just have a single input laser. And so what that means, therefore, is that all of these new wavelengths, they're basically created from optical noise due to the spontaneous Raman emission, right? So you get what you get, right? You have fixed wavelength spacing, right? These are 13.2 terahertz apart in frequency, right? So how can we get tunability, right? Well, what you can do, fortunately, is that if you were to inject a second laser, right? It can be low power, it can be CW or pulsed, right? But if you inject a second laser, right, let's say at 1080 nanometers, that can be amplified, right, through this Raman scattering effect, right? And the reason is because the actual Raman gain bandwidth has about a 30 nanometer range. So you don't have to be right at roughly 1097, is that if you injected, let's say 1080, that can be amplified by the Raman gain of the fiber. And so this seed basically defines the first Stokes line, and then when that gets strong enough, that can sequentially generate the next two Stokes lines, and you can get 1193 nanometers, right? And so the idea is that if you were to vary your input seed wavelength, right, you can vary, right, your third Stokes line wavelength to do some spectroscopy. Right? So that's the idea. All right, so just to wrap things up, right, so we demonstrated an improved laser system for really, I should have said optical resolution, photoacoustic microscopy of lipids, pulse energies of over 6 microjoules at 1215 nanometers. It is scalable to higher energies, mainly because the mode field is bigger than conventional single mode fibers, so they should be able to handle higher energies. And again, as far as really to get tunability, we're going to explore a route where we inject basically a tunable seed laser, right, and that will essentially allow us to sweep the wavelength across the absorption peak of lipids. And just to acknowledge our funding source, and that's my 4-year-old son in the lab, hard at work. But that's it. Thank you very much.